we were writing an equation for a Hamiltonian. The spin and magnetic field vectors are written in the lab frame. The shielding tensor, you only missed 2 words, it's good. The shielding tensor is written in its principal axis coordinate system. And yesterday we spent a lot of time talking about what these are, matrices are, what they accomplish, why we're using them, and why you need 2 copies of them to rotate the principal axis system tensor to the laboratory frame. So these represent a passive transformation, coordinate frame transformation of the tensor going from the PAS to the lab. That's what that subscript PL means. From PAS to lab for the tensor, not the vector, and passive coordinate transformation. Everybody good with that? That's like a 1-sentence summary of what we did yesterday. Everybody okay with that? Any question? Any question at all? Now, the same kind of thing is going to happen for other kinds of Hamiltonians, like dipole couplings, quadrupole couplings. They're all going to look more or less the same. So it's a lot of talk about this, but it will be nice and general. And that's what we call this bilinear rotation. You're going to do it twice to a tensor because the tensor has rank of 2 and 2 spatial indices. Let's move on. This is for Mike. I have this hand-drawn picture because I made the mistake I always rail against for other people. And I had a picture that I grabbed from somebody because I liked it, but I didn't stop and look at it carefully enough. And what I should have done is to draw it myself. So this is my hand-drawn version, and when I have more time, I'll make a nice Adobe Illustrator version. I think it'll be more clear than that thing that I cut and pasted. We have 2 coordinate frames. We have the principal axis system, and we have the lab. I'm going to call the principal axis system XYZ because we're starting there. And it's where the action is. It's the important frame. I'm going to call the lab X double prime, Y double prime, Z double prime because we're going to move to that frame. It's after a couple of modifications on each axis. So XYZ, we always draw it nice and straight. That's easy. This one I had some trouble deciding if I liked what I did or not, but there it is. It's like a basket sticking out of the page, okay? And it's right-handed, I think. So these are 2 frames, and the Euler angles allow you to move this in a set of structured changes until it looks like this, until it sits right on top of that. Okay? So, Mike, so far so good, right? Then, what do we do to get there? How are we going to get there? And the most important thing about the Euler angles, to my taste, if you only understood part of this, if it's too much information for you today and you're still absorbing it, please get this, that the central angle in a 3-angle sandwich is the important one. It's the one you always need. Its name is beta, and it's a rotation around a very special vector that I call n. N is the mutual perpendicular of the initial z-axis and the final z-axis. The mutual perpendicular between those 2 vectors is the only axis that could move you from one to the other with a simple rotation. So the centerpiece, the important thing in the Rose convention Euler angle is to rotate from z to z double prime about their mutual perpendicular, which isn't any of the Cartesian. It's not in the PAS, it's not in the lab necessarily. I'm not going to assume it would be. So this vector n turns out to be an important idea for the whole process. I'm laughing at the font problem when I go to these. Okay. Now, if you had an expression for all of your vectors, let's say you had a PDB file or a small molecule coordinate file, Cambridge Structural Database, CSD. So you had the coordinates for every atom. You can make all of these vectors. I'm going to say this a few times today. So let's say that you're trying to do a homework problem about alanine and you've got a crystal structure for alanine, whatever. You can make the vector for Z. Z in the lab frame doesn't necessarily mean anything in terms of that crystal structure. Or Z in the crystal frame, that's a very specific axis. Right? ABC coordinates in tied to the crystal. And in the PDB file, you could just assume that it's the z-axis that those Cartesian coordinates are written in. So it would be 0, 0, 1. So in that case, instead of being the lab frame, we're picturing that this is a crystal frame. And the z-axis of your interaction, well, it depends on what the interaction is, but a lot of times it's right along a bond. So you can make a vector that connects two atoms. You can take the coordinates of the H and subtract out the coordinates of the N, and you have the NH vector. Sometimes that would be the z-axis of a principal axis frame. So that's something that, in general, you could probably make that vector out of a PDB file, and the details depend on exactly what you're doing. We'll do an example together by the end of this, or in your homework. We'll go over it in homework. So we can make these two vectors literally, a triple number coordinate, Cartesian coordinate. And you can make n then by taking their cross product and then making sure that they're all unit vectors. They should all be unit vectors. The x, the y, the z, x double prime, y double prime, z double prime, n. You want them all to be unit vectors. And you can do that by hand. Now, here's something that I want to point out. In that cartoon, on the last page, and actually in this one as well, perpendicular to the z-axis, I drew a circle. That circle is supposed to guide your eye to think this is the xy plane. All of the x or y vectors, if I would rotate around z, they have to sit in that circle, okay? So I made two circles. I made one for the old frame and one for the new frame. So this circle here, it's more faint and it's in black. It's the circle perpendicular to z double prime. It's the xy plane for the crystal fixed frame. And this vector has a perpendicular circle that's more red. That is the xy plane for the crystal, for the principal axis system, excuse me. For example, the shielding tensor, principal axis system. Go back to the previous, and you see two circles. This is for the final frame, which might represent lab or crystal. This is for the molecular frame, principal axis system, tensor of interest, and the atomic coordinates. So they each have these circles. So now when I put them both together, this is where 3D shading would help. But I've got two circles going on, the larger one being perpendicular to the z, the smaller one perpendicular to the final frame, lab or crystal frame. So you got to use those circles to think about how to do the 3-angle sandwich. So we said that the center step is this rotation about n to move z to z double prime, beta. But I got to get to n. And what I want to do is I want to move my y-axis to n. And there's something that this y and this n have in common. They both sit on that xy plane, perpendicular to z. They both have that property. So it's pretty clear. All I have to do is rotate around z through an angle that we're going to call alpha. They both sit on the same circle. Okay, now I have n all set up. And now I can do that center beta move. And then the final situation, I've got z all lined up, but y is sitting on this thing we called n. It's not in the right place for y, so then I have to do a final z rotation to locate y properly. Now just like I was saying, you can determine beta from having a set of coordinates. You also can determine alpha and gamma. And today I won't say too much about these equations, but if I had a vector for x, y, z, and I have a vector for x double prime, y double prime, z double prime, and that latter thing, usually it's just 1, 0, 0, 0, 1, 0, 0, 0, 1. Then I can take those 6 vectors, and I can calculate alpha and gamma and beta from them. And you might bit of time on your own to look at those equations, see if you understand them, and we'll use them for some homework. But I don't know if I really want to lecture about it. So, anybody have questions about this alpha, beta, gamma, Euler angles? 3 rotation. Yes, please.
I think for figure you used yesterday, it was facilitating x-axis instead of y. So they needed x first, and then for the alpha, and then beta, and then x again for the alpha. But in this new figure, it's using y.
Y, exactly, exactly. And we're going to be using Y.
Rotation. Oh.
Yeah.
So is there a difference between x or y? Or,
You can express any angle either way, and it's just a different convention.
or it should be right-handed.
It should be right-handed, rotations around Y is what we're usually doing. For the Rose convention, Euler angles.
Oh, that is that right-handed? The first one.
The rotation around Y.
Around Z.
So here's the center rotation.
So the first rotation of alpha. Oh, yeah.
And the second alpha. So it'll be, X is here someplace you can't see it very clearly, and then Y, and then Z. And when I rotate about Z, I'm going to rotate in a right-handed fashion. So, so this arrow is backwards, is that what you're saying? Is that what you mean? Yeah, I think you're right. Yeah, good question. No, that's why I can fix it. It's okay. Do you have any other question either, Stu? Alpha sine. Okay, let's keep going. So I mentioned yesterday that normally we're not just going to do one of these rotations, we're going to do a bunch of them. And we might have to go from the principal axis system, determined by the law vectors, to a molecular fixed frame and or a crystal fixed frame, then to a rotor fixed frame, then to a laboratory fixed frame. So what's the purpose to each transformation? The first is so that if you have multiple interactions, maybe you have a chemical-precipitate interaction, and you have a dipole interaction involving the same atoms, and maybe you want to describe their relationship, angular relationship to the next gamut over or something. You put them all in the same frame. So each interaction is taken separately into a common frame. That's the purpose there. The rotation from the crystal fixed frame, you put all the interactions you need together, to the rotor fixed frame is picture that you got a whole bunch of little crystals and you pick up each crystal and place it in the rotor frame. And you're building up the powder pattern, we call it, the powder ensemble. Then the rotor fixed frame has to be related to the lab frame. And that relationship, that angle to relate the rotor to the lab frame is time dependent. And it's especially one of the azimuthal angles, alpha, is time dependent. So you have to do a frame transformation to make the y-axis line up properly on the rotor, and then polar angle, beta, to bring the magic angle up to the lab frame. So that last angle will be time dependent, depends on where the rotor is in its cycle. So we got lots of rotations. I'm showing this just graphically here. You might go from the PAS, and another thing you might do is you might have to dynamically average in the PAS. And then you combine them all into a molecular or a crystal fixed frame, and then you put all those molecules or crystals into the rotor, and then you put the rotor into the lab frame.
Sorry, Ann.
So I alluded a couple times to the idea that you might be able to know what these angles are if somebody gave you a hypothesis, a PDE file and you're trying to fit your data to that hypothesis. For example, from the PAS to the crystal fixed frame, especially for that step, you could derive that from the coordinate numbers. Okay, the Cartesian coordinates, you can get the right Euler angles to relate it to the crystal fixed frame. Some of these other angles, there's no right answer. Crystal fixed frame to the rotor, well, you're going to randomly pick angles and add up lots of different crystals. The rotor to the lab will be doing that problem, so it has a deterministic value. Where alpha is a time-dependent number, linearly time-dependent, and beta is famous. And remember that when you put all that together, rotation around z through alpha, around the new y through beta, around the new z through gamma, that you get this mess. Now we can use that, we can do some problems with it, but we're not going to want to do that if we have a whole bunch of rotations that we need to do. So that's where we ended. We said we need some simplifications. Now we're going to introduce, I think, the most simplified version you could have. I don't think there's any further simplification from what you could do with a spherical harmonic. So any more questions about that other material? And I want you to know I'm going to talk until about 2 o'clock, and then we're going to have a problem session today with Art, some of the solution problems. And hopefully next week we can have a problem session on some solvents problems. There's a lot of problems in the handout, you can look at them ahead of time. And I gave you a choice. Which problem do you want to do? You can choose. And also, throughout my notes, I'm flashing questions to the student in red. You can pick one of those. Okay, so you get some choice on which problems you do for the solvents problem. But I would like you to try to come with a solution to one of these problems or a question or this kind of. So we want to simplify this thing, and here's what we know. We know that a lot of times the frequencies only depend, in terms of the Cartesian representation, it only depends on the ZZ term. That 3 by 3 matrix, we're doing a lot of math, and all we really want is that 3, 3 element down at the bottom right. We also know that we tend to do a lot of rotations around Z. A lot more of them than anything else. So knowing those two things, there is a best way to do this. And I'm going to motivate you with just a couple of observations.
Yeah, no, somehow I've lost my ability to do something in, and I can't recreate it. So just carry on.
We're having a comedy of errors with Mike and me and Suresh. It's going to be good. By the end of the term, it's going to be very, very good. Okay, so first thing I want you to think about is this decomposition of sigma. We're going to decompose a 3 by 3 arbitrary 3 by 3 matrix. There's no rules with sigma that x, y, x to be y, x. No, there's no rules. Think of 9 arbitrary numbers in this matrix. And I want to decompose them in terms of component matrices, like a basis set, to expand in terms of component matrices that'll have really nice properties. Since they're 9 arbitrary numbers, in the end we need 9 basis matrices, but I'm going to start slow. So here's my 9 arbitrary numbers, and I want you to think of them as being a symmetrized version and an asymmetric version. Symmetrized version would have the entries on the diagonal, as usual, and then I average across the diagonal for these 6 elements. So that now there is some symmetry in this problem. The asymmetric would be to take the differences across the diagonal and normalize properly by 2. If I add these matrices, I get back what I have. But they're going to have really different properties, these 2 matrices. And it turns out the properties are different in terms of rotation, such that this behaves like a vector when it rotates. It actually only needs 1 copy of R in a sense. And this thing behaves, strictly speaking, like a tensor. And it has a part that's rotationally invariant, and a part that acts like a d orbital when it rotates. Let's see what that means. So we're decomposing it. And the first thing to note about this decomposition is the following. Remember that we only need this for spectra, sigma 3,3 in the lab. We only need the 3,3 element. So we do all this rotation and we only pull the 3,3 element. You're not going to get any 3,3 element from this matrix, ever, in any rotation, in any front. That's something that you might want to confirm. You can approach that in a variety of ways. But by construction, since it's anti-symmetric in terms of reversing the spatial indices, it can't have any 3,3 element, or 2,2 element, or 1,1 element. So this symmetrized version has all the information for a spectrum in it. So when we go to measure a frequency, you could use sigma or you could just use this symmetrized version. It should never make any difference. Now the same may not be true for relaxation. That's another way of saying when people do spectroscopy, they don't access these anti-symmetric components. It just won't show up in the spectrum, might really be there, but they won't be able to measure it. So now that you have a symmetric matrix, what's so nifty about that? Why would we want to go to this trouble of symmetrizing it? Because a symmetric real matrix can always be diagonalized. So you realize that the symmetric part can be summarized with very few numbers. There's an isotropic shift in there, and there are two other pieces of information. We call them delta and eta. So if it can be diagonalized, it only has 3 pieces of information. And we tend to think of them as the trace, which doesn't change on rotation. The sum of the diagonal elements doesn't change during rotation. It's a rotational invariant. And it's not really a vector at all. It doesn't rotate. It doesn't have a direction in space. The trace is like the s orbital. Everything you do to it still looks the same. That's one piece of information. And then delta and eta can be used to describe everything else on the diagram. So if eta were 0, you have delta minus half delta minus half delta. That's traceless by construction because we took the trace out. And it has the look minus a half to 1. If eta isn't 0, it means that the x and the y axis can be distinguished. That's what it means physically. And so then you have this symmetric, traceless, diagonal form as given here. Now, when people talk about tensors in the literature, quite often those are the 2 numbers they're going to give you. That's why we're taking time to look at it in this form. If I had a new functional group and my protein and nobody had ever described it by solid NMR before and I wanted to tell you about the tensor elements, I would not be giving you 9 arbitrary numbers in some crazy frame. I would be giving you delta and eta. And it has a nice relationship to the appearance of the spectrum. Let me see if I can quickly bring that up. Let's see sample spectra here, yeah. All right. So for this tensor, for example, maybe the isotropic shift would be here someplace. It's sort of the center of this tensor. And delta might be this extreme element, and minus delta over 2 here would be the case for the x and the y axis. And so they're more probable because there's more ways to be along the x and the y axis than there is along the z axis. So people report those kind of numbers, delta and eta. They don't report the entries of the tensor.
And when you see the delta for a plus battery is equals to 0, you mean the trace of it.
If delta were 0,
But
then it would be isotropic.
So the last the slide 4 is you're seeing the tensor for asymmetric 0. You mean the trace is 0 or
just the 3-3 element. Just the 3-3 element. Always 0. So that's even if you rotate it through any arbitrary angle. The way we constructed it was by saying that you take the difference across the diagonal. So just by assumption, you're not going to have anything on the diagonal. And it's also the case that if I take a tensor that has this form, x minus x, y minus y, z minus z, and zeros here, it doesn't matter what angle I rotate it through, it will always have a 0 here. That's what I'm saying. And I'm suggesting if you want to look at that and try to prove it to yourself, that's a nice exercise. So the asymmetric tensor never influences spectrum. It's only the symmetric, and we know that the symmetric can be diagonalized, and that's when you realize, oh, there's only 2 numbers in this game, delta and eta, that's all. When you diagonalize the tensor, we've identified the z-axis, so whatever rotation it took to diagonalize that tensor, in the new frame, z is a special high symmetry axis of the molecule. So once it's diagonalized, let's say you started in an arbitrary frame, you're making measurements, and all you know is the orientation of the crystal. So you get 9 numbers, and they're 9 numbers relative to the crystal. If you were to diagonalize those numbers, you're identifying the directions of the tensor in the principal axis frame. The rotation that accomplishes that diagonalization answers the question for you, what are the directions of this molecule? What are the principal directions for the shielding? So in the old days, I don't know if I have maybe one of these rotation plots, a lot of work that was done in Wa's group, in a little bit in Griffin's group. I don't have one of those plots here. Maybe not. Maybe I took it out. I think it's in the figure in your handout then. It shows an experiment in which you have a goniometer. In the magnet, typically inside the coil. That's too bad it wouldn't have. So typically, you'd have like a goniometer that allows you to rotate the crystal along any arbitrary axis. All that would be inside, sample would remain inside a coil, inside a magnet. And so you could rotate your crystal. You mount it knowing where the crystal XYZ axis were. And so you would have a series of measurements where you're modifying one of these angles of the crystal. And you get chemical shifts, and you get oscillatory chemical shifts. So this is the crystal relative to the field. And this is the shift that you record. And you can rotate in all 3 directions, and eventually from that you could build up this matrix of 9 numbers describing the symmetrized chemical shift tensor. And if you were to diagonalize that, the angles involved in that frame transformation to make it diagonal would tell you exactly what the orientations of the principal axis was for that interaction. So when we write it in this diagonal frame, ZZ is some special axis in the molecule, for example, a long bond or perpendicular to pi orbitals. It's always some high symmetry axis for that function. So in that exercise, we just took our tensor 3x3 matrix and we separated it into asymmetric and symmetric. And we realize all we need is the symmetric. It can be diagonalized. The whole thing can be summarized with 3 numbers instead of 9. We can go further with this kind of thinking. Basically, the isotropic shift, the trace of the matrix, it has a special role. That's the shift that you measure in solution. And I like to make the analogy with an s orbital. It is a mathematical object that is just invariant with respect to rotation. And in tensor notation, we call that L equals 0. It means it has no angular momentum, doesn't need to be rotated. Has the same value. Even if you rotate the molecule, you don't have to rotate it. It has the same value in all frames. Then you have a second piece which corresponds exactly to that anti-symmetrized tensor. And we say that it has L equals 1, like a vector, or like a p orbital. And it doesn't contribute to our measurements, so we typically ignore it, but it's there. And then you have a symmetric tensor, which behaves like a d orbital, or an object with L equals 2, and it needs 2 copies of R to rotate it. So we're going to separate our tensor into those pieces. The s orbital-like piece, L equals 0, the p orbital-like piece, L equals 1, d orbital-like piece, L equals 2. And that's the most basic dissection that we're going to use for constructing the spherical harmonic coordinates. We're building up a basis set to write any tensor. Besides this separation, we need to think about one more thing. There's only one L equals 0 component. It turns out there are 3 L equals 1 components and 5 L equals 2 components. So overall you have 9 spherical tensor components. And an intelligent choice for those full decomposition is to think about the fact that we do a lot of z rotations. So here's a nomenclature. We're going to have basis set elements, matrices, that we can use to express with linear combinations any arbitrary matrix. And those basis set matrices will have 1s and 0s in them, and they go with this nomenclature. Each matrix is a T with a unique combination of L and M. So L corresponds to what we were just talking about. L might be 0 if it's rotationally invariant, 1 if it rotates kind of like a vector, and 2 if it rotates kind of like a tensor, like a dipole times another dipole, like a d orbital. And when, so L could take 0, 1, or 2. It takes these 3 values. But for each value of L, M can take a value from minus L to plus L. So that's, you have 5 for L equals 2, 3 for L equals 1, and only 1 of them for L equals 2A. Let me just put the answer up here, and then talk about why this is like the most brilliant way to decompose your matrix constant. So one of the matrices will be this. That's rotationally invariant. Another one is this. That's an object that rotates kind of like a vector, more so than like a tensor. 2 more of them are represented this way, that one of the 2 takes the plus sign here and the minus sign here, and the other takes minus and plus here. Another element is this, and then 4 more, 2 here, 2 here. And that's basis set, by which I mean any tensor you could write down with any arbitrary 9 numbers, you could express as a linear combination of this basis set. Now you'll know it's a good basis set if they're all perpendicular to each other, if they're all independent of each other, if they're all orthogonal to each other. Do you know how to check if that's true? I have 9 matrices, and I'm saying I'm going to use them as a basis set to express any arbitrary matrix. And since there are 9 elements and 9 basis sets, that's perfect. There's just enough information if and only if they're all perpendicular to each other. They all have no overlap. Do you know how to do the overlap between 2 matrices? Do you know what that means? If I asked you to do that with 2 vectors, would you know what it meant? I've got 2 vectors, and I want you to tell me if they're linearly independent or orthogonal. How how would you do that? Dot product, inner product, thank you. So that's the same thing here, and I'll remind you how to do that with the matrix. But the idea here, I'm going to take my matrix, and I'm going to take the inner product with T00, and I'll get an answer. I'll take my matrix, and I'll take the inner product with T10, I'll get an answer. So instead of that 9 by 9 matrix, I can just list out what are the components of each of those tensor basis tensors. So each entry in this vector M, in the spherical harmonic notation, will be the inner product of the Cartesian matrix in its original form and the corresponding spherical harmonic. Just another way to write your matrix. It's a basis set for your matrix. And that inner product, when I take M and I combine it, for example, with TLM, T00, it's a kind of multiplication. It's an inner product or a dot product, or some people call it a Frobenius product. I'll be writing it with a colon, 2 dots, because it has 2 spatial indices. So as a vector, I do A dot B. And all you do, just like with the dot product of a vector, A1, A2, A3, and I want to dot it to B1, B2, B3. I'll get A1, B1 plus A2, B2 plus A3, B3, right? So I get a scalar. I just get a number out. There's no vector anymore, right? Same thing will happen here. We start with 2 of these 3 by 3 matrices, second rank tensors, and when I'm done multiplying them with each other, I'll just have one number. I'll just have a scalar, and pairwise I'll combine them. But there's one detail that I don't want you to forget because you lose a lot of time if you forget it. This basis set allows you to write complex numbers, not just real numbers. Most of the matrices we're going to be talking about for the principal axis system interactions, the spatial terms that describe the molecule, like chemical shielding or dipole coupling. Most of those are just real numbers. But we've got a basis set here that involves complex numbers. So we can express things with complex numbers as well. You'll see later where we're doing that. When I take the inner product of 2 matrices, I do need to take the complex conjugate of the second one. So it's same thing would have been true for a vector if it had a complex number in it. I would need to do B1 star, B2 star, B3 star, okay? So you see a complex number there, and remember that the dot product, take the complex conjugate second. Yeah, so we can use this basis set to express any arbitrary 3 by 3 matrix, any arbitrary second rank tensor. It's synonymous in this case. And we would take our tensor and we would take the inner product with each of these to find out whether that spherical tensor component was present in the tensor. So you could say about a tensor that it's traceless, it has no trace, if you multiplied it by M00, took the inner product and got 0 for the answer, that means it's traceless. Okay? That means you don't have any isotropic shift if it's an NMR problem. You could take your matrix and you could take the inner product with M20, and you could find out in that frame what's going to come up for sigma 3,3, which I remind you is the only number we're interested in this game. We don't get that interested in the isotropic shift because you don't have to calculate anything because it doesn't rotate. So we usually leave that out. We don't get involved with these ones because we know that anti-symmetric tensors cannot contribute to your experiment. So basically, if you want to know what the measurement is in the lab frame, you just need to put a circle around this number. So you just need to project onto M20, and then you work with a very symmetric matrix, very sparse, very little information, It's going to be nice to decompose your matrix in terms of these tensors. But there's even more to it that simplifies things. Now this slide, by the way, has a few other things in it. And I put some of this information on the bottom of the handout after I gave it to you. So I'm going to give you a modified handout in a little while, a day or two. Just, this is something, just reminding you of some math that with two vectors or two tensors, if you like, you can make an inner product, you can also make an outer product. We need to do that very soon here. We're going to do it in just a minute. You also can just multiply them, and that's what we've been doing with this, row column multiplication. And outer products make bigger tensors with more indices. Inner products make collapsed tensors, typically no indices, just a scalar. Regular matrix multiplication usually preserves the rank of the tensor. So if it's a second rank tensor, 3 by 3, after you multiply it with another one, it's still a 3 by 3. I think it's helpful to take a minute and just review, for yourself, these different ways to combine two tensors, because they're utterly different, but they look a little similar on the page. And if you're going to be using something like Mathematica or MATLAB to sort out what's the command to do this kind of multiplication, because MATLAB will do all of it. So this is just a star in MATLAB. This there's a variety of ways you can do it. This is really good at matrix manipulations, but one way you can do it is just say dot of A and B. This outer product can be done with the command clone of A and B, or it can be done in other ways. So those are three really different combinations of two matrices. Just to sum up where we were, we have a basis set by which we can express any 3 by 3 matrix. It's 9 linearly independent orthogonal matrices that span the space. That means they can be used to express any combination. But they're neat. They're the best basis set because they're organized according to their rotation properties. The invariant, the vector-like, which is a first rank tensor, and the second rank tensor, L equals 2. I could be over. And once again, I know I said this before, but to say that they're linearly independent, that's a really easy thing for you to confirm. You can take any two of them that you want, do their inner product, and if you don't get 0, complain to me. Either it's not true or I have another typo. Okay? That's one of the recommended homework problems. Just show me that they really think that they're linearly independent, because they aren't a good basis set if they're not linearly independent. Now, they're clever in another way. It's not just any old basis set, and it's not just that we've organized it into invariant vector tensor, but every single one of them is a very special thing called an eigenoperator of RZ. What that means is that if I take that tensor, any one of them, 2, minus 1, any arbitrary one, if I take it and I rotate it around Z, I get the same thing back with a number in front. How easy could a rotation be? I mean, what would be better than that? Nothing. That's like perfect. So every time you need to do a Z rotation, if you expand your tensor in terms of these, you have no math, nothing. You just put e to the minus I alpha in front of it and you're done. So decomposing the tensor, maybe it sounds like a little bit of work, but I'm going to try to persuade you in this last segment that it's exactly what you needed to do anyway. Here's an example of rotating T00. So in another homework problem I ask you, go ahead and rotate these things and show me that they are eigenoperators of RZ. Show me that when you apply RZ to any of those 9 matrices, that you get the same thing back with this. See if it works. And if it doesn't work, it'll be a learning moment for one of us at least. So here's this is the form that T00 has, except it has a scaling constant on front, which I removed. And here's what it would be like to rotate it. I would put this R inverse in R, okay? So it's sandwiched. And I'm claiming that when I do that, I get back the same thing. That doesn't even have an extra scaling factor because it's not just an eigenoperator of Z, it is actually an invariant. So you don't even get that number out front. If you do this exercise for R10, I expect the same, that you'll get nothing up front because M is still 0. But if you do it for the 1 minus 1 tensor, you should see some stuff appearing out front. So pick 2 of them. Don't do them all. Just pick 2 of them. See what it's like to do it with the help of something like MATLAB if you want. Or just pick something easy enough that you can do it in pencil and paper. But the important thing is it just tests whether you're really following what we're saying here. So these are eigen operators of RZ. Every single one of the spherical tensor harmonics expressed this way, like making them clear in 3 by 3 tensor form. You can see that they are eigen operators of RZ. Now you can go back, if you want to show yourself that not everything in a Cartesian basis set is an eigenoperator of RZ. I think it's sort of intuitive. Once you've done some of these spherical tensors, you see how elegant it is, how everything disappears, and all you're left with is the same matrix with something out front. But if you would pick up an arbitrary Cartesian matrix, that's not what happens. You're going to get this whole mess of alphas and betas and gammas and so on, okay? So it's a very special property of these tensors. So instead of doing all 9 of them, you might do 2 of them, 2 of the ones that have M unequal to 0, and then you might pick up an arbitrary matrix, and it's not going to work. You'll see that it's alphabet soup. Okay, so I think that's a nice homework. That's of the homework problems. If I were you, I would pick that. So we have taken the 3 by 3 matrix or tensor that represents what goes on inside the molecule, the shielding and susceptibility, the dipole couplings, and instead of writing it as a 3 by 3, I'm recommending that we're going to be writing it as being in this basis set. You say how much of T00 is there, how much of T10. But the truth is that if we're going to do that with the chemical shielding tensor, we're going to have to do somehow the same thing to B and I. So just like when I said you can't write a Hamiltonian and you're using the principal axis system for the CSA, but you want to use the lab frame for I and B, that's not right. You can't do that. You're going to get everybody in the same frame. The same is true here, that if you're going to write this Hamiltonian that we've been working on, you should have it up on the board all the time, but just to remind you, the last time we had the full Hamiltonian, it might have been the first slide. Just like we have to have this and this and this all in the same frame, we also have to obviously use the same basis set to talk about them. We can't decide that spherical harmonics are a nifty idea here, but we want to keep these guys Cartesian. That's not going to work. So how are we going to write B and I in this new basis set? Well, that's easy, and it can be done a lot of different ways, and it has a big benefit if you start to think about it. So both the spin and the spatial terms can be thought of as second-rank tensors, in a sense, equal footing, because instead of keeping these separated as vectors, like a sandwich in your Hamiltonian, you can combine them into a second-rank 2 indexes, 3 by 3 matrix. And that's where we use the outer product. We were just talking about the outer product a minute ago. So B, outer product. And the outer product of any 2 vectors, U and B, will always be a tensor, like if 2 vectors, you'll make a tensor. So the vectors are rank 1, the tensor will be rank 2, it'll have 2 spatial indices. And its entries are given by this really simple rule. The matrix ij element, you just take the ith element of U times the the jth element of B. You just combine those two, regular multiplication, and that's the entry there. So let's say I had start with the 1 by 3 and another 1 by 3. have V1U1, and I can have V1U2, V1U3, and so on up to V1, V3, U3. So you can make a second rank tensor out of the two B and I. There's two vectors, B and I. You can make a second rank tensor out of it. And then that's useful because it allows you to notice some really powerful simplifications when you combine it with the chemical shielding tensor. So I'm making this assertion here and I'm asking you to confirm it. That's my second favorite homework assignment. As I mentioned, you don't have to do all of them. I came up with like 12 or 15 problems. You don't have to do all of them. But if you want practice with these kind of manipulations just to get more comfortable, we've been writing this all along. This is a vector, this is a tensor, this is another vector, and after you're done with the whole thing, you've got to scale it, right? You can do it this way, but I'm saying it's exactly the same, by definition. To take the outer product of B and I, second rank tensor, and then do the inner product of that on sigma. They mean the same thing. Just write out the terms that come up in a generalized case. Don't pick a specific case, but just have B, 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 X, B, Y, B, Z, and I is I, X, I, Y, I, Z, and just multiply it all out, and you'll see that they mean exactly the same thing. And that's a useful thing to do. That's a useful thing to do. So now we'll be able to pick out the parts of sigma that would ever end up in our experiment, and we'll know which of the spin operators that matches with. So I have a solution here, but we're not going to look at it until you get a chance to think about it. So we're organizing the spatial degrees of freedom, dipole coupling, CSA, in terms of the behavior, in terms of the angular momentum. Is it an L equals 0 invariant? Is it an L equals 2? Like two spatial indices. We're organizing the CSA tensor that way, and we're going to organize the spin degrees of freedom that way as well, B and I.
Is M a vector?
Which?
Is I a vector?
Yes, it's a vector. We talked about that a little bit last time. It's a vector whose entries are IX, IY, IZ. Each of those is an operator, so it's a vector of operators.
So I think it's need to be transposed to general figures. But maybe add.
Oh, all along I has been a row. B has been a column and I has been a row.
Oh.
So maybe that would be clearer if I write that explicitly. It's a good idea. But all at the beginning I just said let I be a row vector. They could all be by default column vectors, and then I could call it I transpose. That might be better. I is column. I either have to remind you or call it I transpose. So usually when you read papers about solid-state NMR pulse sequences, if they're talking about the tensor that describes the spin, like this tensor here, B, outer product of I, they call it TLM. And if they're talking about the molecular degrees of freedom, the CSA, the dipole, they usually call it RLM. But there's no really hard and fast rules in terms of this nomenclature. But I'm going to do that because it's what you see most often. So if I'm talking from here on out about a TLM, that means things like spin operators in the magnetic field. If I talk about an RLM, that means the dipole coupling, CSA, the things that are attached to the molecular degrees of freedom. Now, when I combine them, if I take TLM and RLM, what am I doing? If I take TLM and RLM, which is basically what we're doing when we go when we say, let's do this calculation, B cross I dot sigma, and we're saying that's the same as doing B sigma I. If I'm going to do that with spherical tensor components, there's a huge advantage. This is where you get a real payback from having picked this way of expressing things, that I'm only going to get something non-zero when L and M match. So if I take in the spin degrees of freedom, L equals 0, so M has to be equal 0. But in the spatial degrees of freedom, I want to pick something like L equals 2. I know the answer is 0. And there's something very intuitive about that. I picked a s orbital here, and I asked for the overlap with a d orbital. And it's just a symmetry argument. Okay. Take an s orbital, and I try to find the overlap with the p orbital. The answer is going to be 0 every time. So if I take different values for L, it's quite obvious that there's no non-zero resultant to that inner product. But it's also true that M has to match, which may not be that obvious at this point, but it's true. So you don't get any resultant in this calculation unless the spherical tensor components are identical. So that means the following. If I only measure along Z in terms of the B vector, the I vector, that's what we talked about in the first class, the truncation and the simplification. It also means that for the spatial degrees of freedom, I'm only going to keep track of those elements, those 3, 3 elements, or L equals 2, M equals 0 elements. When I combine two tensors, L, T, L, M, M, L prime, L prime, they'll have their components, but I don't do any of these kind of cross multiplications. I just sum M, L, M, T, L, M from L equals 0 to 2 and M equals minus L. Just match them. That's all. Don't multiply anything else. So that's a little easier than multiplying 2 3 by 3 matrices. There's a lot less operations. And the benefit is better than that because, as we've been discussing at length, most of the time we only want this one. For relaxation, there's still an advantage. There's still a big advantage, but it's not as crazy as just saying, okay, I'm down to multiplying. So as soon as I know how to write M and T in spherical harmonics, I'm down to multiplying two numbers, and that's it. So we spent a lot of time building up to how could we rotate a matrix with Cartesian. And we know a lot already about rotating these spherical harmonic components. So if in the laboratory frame, I know the value for this element, for example, how could I relate that to some other frame? How can I rotate it? How can I make a frame transformation for the spherical components? We're going to use those Euler angles, the Rhodes convention. So rotating around Z is really great. But all I'm going to do is rotate around Z, and get the same thing back, no change, and I get the space back of e to the minus I m alpha. If I rotate around Z, again, the third operation in the Rhodes convention, it's just e to the minus m gamma. So Z rotations, there's really nothing to do. And the Y rotations, we typically look it up. It's a function of beta. It's a polynomial function of beta. I have it in the notes. So you have to only concern yourself with L equals 2 tensors. We're not using these rotations for L equals 1. Only changes in rotation. We're not using them at the moment for L equals 0. I mean, nothing changes. For L equals 1, we're omitting that because we think it doesn't contribute to our measurement. So you only need L equals 2. Then you have to see your rotation here will result in having a little bit of some other tensor element. It has to have L equals 2. It just has a different value of M. It just has a different value of M. So you'll generate a little bit of, let's say I have, as I mentioned, some value in one frame for T20. I rotate and I go to another frame. I might get, create some component of L equals 2, M equals 1, M equals minus 1, M equals 2, M equals minus 2. So I begin with just purely this term, and after rotation I might make these, never make this, or this, or this, or this. So the question is, if I rotate around Y, how much of these other spherical harmonic components do I make? That's the functions that was in that table. That's the answer to that question. If I rotate, and I begin, for example, with L equals 2, M equals 0, this is the answer to how much of L equals 2, M equals 0 I'm going to have after the rotation. It's a very famous function called the P2 cos theta, or the second Legendre polynomial theta. So if I rotate through an angle beta, this is how much will be left of that spherical tensor. Well, what happened to the rest of it? I'm going to be generating these other tensor components, 2, 1, minus 1, minus 2, according to these trigonometric functions. According to sine squared of beta, I generate the M equals 2. According to sine of 2 beta, I generate a little bit of M equals 1. So what happens on a rotation with spherical harmonics is that you mix various values of M in linear combination. But it's really easy to make an expression of that because all you do is you look it up on this table. Someone else already solved what the function is, and then you're just going to plug in beta. So that tells you how much of all of these other terms can be made if you start with this term and you rotate. So when you do a rotation with the spherical harmonics, two of those three angles can be done by inspection, either the IM alpha, either the IM prime gamma, and the third can be done by lookup table and just plugging in. So this is a rotation matrix for a spherical harmonic. It takes a component with L equals 2 and a certain M value, and it tells you how much you make of another M value after the rotation. Here's the whole equation. Writing my tensor in spherical harmonic notation in a new frame, what I have to do is I have to write it in the original frame and specify which component I want. And I'm going to march through those various components, and the size or amplitude of each of the components will be given by this expression. So I begin with L equals 2, M equals 0, and this kind of equation tells you how much you'll end up with for all the other spherical tensor components when you're done. So the set of tensors is complete, so for sure it's someplace in there. Rotation by RZ just gives you back the same tensor, so that's easy. But when you rotate around Y, you mix values of M. Then I'll share the same value of L. So that's a good starting point. We covered quite a lot today. And I think this last bit, how to write the rotations in the Wigner elements, we'll have to start with again next time. We'll start with it and see if we can get some questions going. That'll be next week. And I recommended a few problems for you to do. You want to be able to take a little break before